So this is an advanced higher chemistry video, and we're going to be talking about what are synthesis reactions and getting used to using arrows in synthesis reactions, because arrows and the attention to detail in arrows is important at advanced higher. So synthesis is by far the biggest and by some people considered the hardest section of Unit 2. There's a lot of information and things need to be very specific. Now, synthesis covers the chemistry of making one type of organic molecule from another and understanding how to go from one functional group to another, often in a series of steps, and being able to identify and know the reaction conditions involved in each one of those steps. There are many types of reaction to learn, and synthesis, as I said, can involve up to 3 different steps in a row. Sometimes you will be told the steps, sometimes you will be given the starting molecule and the end molecule and have to work out what goes in between. Sometimes you're given the end molecule and you have to work backwards to how it could have been made. So it can be quite complicated. Now, mainly what we're going to focus on in this video are bonds and the way that bonds are broken and reformed and how we use arrows to represent this. So the first thing we're going to look at is bond fission. Now, if you do physics, you should be familiar with the words fission and fusion. If you do chemistry, it's probably the first time that you've encountered these words. Fission means breaking. So bond fission means breaking a bond. Anytime we're doing a chemical reaction, bonds must be broken in order for new bonds to be formed. So typically bonds in the reactant or reactants are broken and bonds in the product or products are formed. Breaking bonds is called bond fission and making bonds is called fusion. And there are 2 types of bond fission. Now the main one that you've looked at in higher is what we would call homolytic fission, and that is the type of fission that led to the formation of free radicals. And that is where a bond splits equally, where both electrons end up on each, one electron in the covalent bond ends up on each atom. The alternative version of fission is heterolytic fission, and that's where a bond splits unequally, generating 1 positive ion and 1 negative ion. So you are familiar with heterolytic fission, you've just never really heard it called that way before. Now in homolytic fission, we have our bond, and we can see that bond breaks equally, and we see 1 arrow going to the atom on the right, 1 arrow going to the atom on the left, and we generate free radicals. Now we know that this process is typically caused by UV light, but there are other conditions within a chemical reaction that could cause this to happen. And it's always, when we're talking about fission reactions, we're typically only talking about a sigma bond where you might be asked to represent the fission. So the sigma bond splits evenly and each atom keeps 1 electron. This type of fission is really only likely to occur within non-polar bonds where the electrons are evenly shared between the 2 atoms. So where there's a low difference in electronegativity or no difference in electronegativity. And you result in 2 radicals, and radicals, even though they have these unpaired electrons, each atom overall has no charge, so they are neutral. Radicals are highly reactive and unpredictable, so they're not very good at doing a controlled synthesis reaction. So you don't really want to generate radicals if you're wanting to do a controlled synthesis reaction. What we'd be wanting to do instead is heterolytic fission and heterolytic synthesis. Now in this one, we can see that the bond is breaking and we've only got 1 arrow. That arrow is going from the bond, where the electrons are shared, to the atom that ends up negatively charged. And what's been left behind is the A atom becoming positively charged. Now in this case, the sigma bond splits unevenly, 1 atom is gaining both electrons from the bond. This type of fission typically only occurs when you have polar bonds, and it results in you obtaining oppositely charged ions. it is much more controlled. We will always know what a positive ion will do and what a negative ion will do, because opposites attract, like charges repel. So if we generate ions, we can better control what those ions will then do. So this is the type of fission we want in synthesis reactions. And pretty much every example from this point onwards, we will be looking at heterolytic fission. But you do need to know that homolytic fission, because you can be asked to draw and explain it. Now, if we compare those two reactions side by side, those two types of fission, and we look very carefully at the arrows, we can see that the arrows are slightly different from one another. Not just the number of arrows, but the way the arrow is drawn. In the top reaction, our homolytic fission, if you zoom in at the arrow and look particularly at the arrow head, it is only a single-headed arrow. That is because one electron is involved in that single arrow head. Whereas in our homolytic fission, we can see it's got a double-headed arrow, and that is because two electrons are moving. The other thing about these arrows is that they are always showing where the electron starts and going to where the electron ends. So the start of the arrow is where the electron starts, the end of the arrow is where the electron ends up. For every one electron, you get half a head. So if you've got a double-headed arrow, that means two electrons are moving. If you've got a single-headed arrow, that means one electron is moving. And really pay attention, that arrow is always ending up on an atom. Electrons never just end up nowhere in blank space. You have to show it going onto an atom, and they are always starting at the bond, because that's where the electrons start. So within our synthesis reactions, we need to always be aware of drawing our arrows correctly. Straight arrows and even reversible arrows, they indicate transformations, they indicate that reactions are occurring. Our curly arrows indicate the movement of electrons, and that's when we're going into more detail about how or the mechanics of a reaction. The arrow always starts at the source of electrons and ends up at the destination of the electrons. Your single-headed arrows are for the movement of single electrons, double-headed arrows for the movement of pairs of electrons. In homolytic fission, it's always going to be single arrows. In heterolytic fission, it's always going to be double-headed arrows. And as I said, in all the examples of synthesis reactions that we're going to be doing from this point onwards, it's going to be heterolytic. So you will be using double-headed arrows. Now, homolytic fission always requires two arrows, starting at the bond, ending up at the atoms, or radicals, that's what we would call them. To show a bond forming from radicals, so doing a fusion reaction, we need to show that the arrow is going towards the empty space between two atoms. So in fission, we start at the bond, end on the atoms to form radicals. In fusion, when we're forming a bond between two radicals, we are going from the radical to that space between the atoms to show a bond is forming. Showing the same thing with heterolytic arrows, you only need one arrow. It goes from the bond being broken and either ends on the atom that will become negative or the space where a new bond will form. So you've seen the fission, here's the fusion. So if you're going from A bonded to X and you're doing a substitution reaction, you can draw that arrow going to the space between X and Y. It is also acceptable in this case to show the bond, the arrow ending on Y, but it's technically better to do it in the space between the two.